All right, 123 here. Take this with you. Let me clear it out. Right. So if you did physics, you're going to recognize a lot of this. Some of the notation might be slightly different. Let's go ahead and start with the idea of what a vector is. So to define vectors, it's useful for us to first talk about scalars. Scalars are what you think of when you think of numbers. You've been working with scalar numbers since you've been learning to count. So scalars are numbers that count things or measure things like magnitude or size. So some examples of things that we do with scalars would be like length, area, speed is a scalar, weight is a scalar. So if I say my backpack weighs 42 pounds, that's a scalar. For those who've been in physics, what's the difference between a scalar and a vector? What do you remember? Yes, so a vector also has a magnitude, but it also includes a direction. So a vector gives information about a magnitude and a direction. So some common things that we measure with vectors would be velocity and force. And a lot of times we use vectors for position as well. At some point in science, they probably taught you the difference between speed and velocity. What's the difference between speed and velocity? They're not the same thing. Anybody know an example? Yeah, what do you remember? I think you might be thinking of force, maybe. So the difference would be if I say I'm in my car going 70 miles an hour, is that speed or velocity? That's speed. If I say I'm in my car going 70 miles an hour due south, that's velocity. Velocity has a direction involved with it as well. So in order for two things to have the same velocity, they need to be going the same speed and in the same direction. All right, so we're going to look at some visual representations of vectors, and we'll focus a lot on that in a future lesson. But for today, we're going to be doing mostly kind of an analytic representation of it. But let's start off with a visual representation. So I'm going to draw myself an XY axis. And if you don't have grid paper, that's okay. You can fake it. We're going to need 4 tick marks in each. Yeah, just in the 2 positive directions. That'll be good. So I'm going to give you an example of a vector. This vector is in a particular notation. Those of you who've taken physics can tell me whether this looks familiar to you. Have you seen this notation for a vector before? Physics folks? No, this is a little different then. Okay, that's fine. That's fine. This is kind of a more mathematical notation, or at least I've seen it more often in math textbooks. I'll also show you the engineering version that has I's and J's in it. Physics people, did you use I's and J's? No? How did you do vectors? You didn't do it. Did you draw like arrows and find X and Y components and stuff? Okay. Yeah. Free body diagrams. If that sounds familiar, we'll be playing around with those a little bit. All right. So well, here's the idea. So this is going to give us an X and a Y component for a vector. So this vector is going to be heading in the X direction by 4 units and the Y direction by 3 units. You can actually just take and plot the point that would be 4, 3. So pretend those were parentheses instead of brackets, and then connect it from the origin. And the thing that makes it, because it's a vector, I do need to put an arrowhead at the end of it. So 4, 3 is telling us X and Y components for this vector. So it's giving us X and Y components, and we can kind of think about this 4 being the X component and this 3 being the Y component. All right. Here's the thing though, when we talk about vectors, it doesn't have to start at the origin. So 4, 3 could be any vector in any location as long as it's going over by 4 and up by 3. Okay, so if I wanted to, I could start this vector over here. And I could go over 1, 2, 3, 4 and up 1, 2, 3. And I could draw that vector. And you can see that it's the same length as the one that I drew before. It's heading in the same direction, so it is the same vector. I want to pause for a moment and talk about some of the tools that we've learned in the past. Could you the magnitude of this vector? And magnitude is kind of just a fancy way of saying length. We know that it's 4 over and 3 up, but the magnitude would be how far is it along the actual direction of it? Do you know what it is? It's 5. What were you going to say? It is 5. What tool could we use if the numbers weren't so easy and we didn't recognize a 3, 4, 5 triangle? What tool? Yeah, so we could use good old Pythagorean theorem to find this. If we didn't know what this was, we could set up an equation and say, I'm going to just call it C. We could set up an equation and say 3 squared plus 4 squared equals C squared and solve that. And that would give us our magnitude. If we did solve that, we would end up getting C equals 5. So the magnitude of this vector is 5. And since this is also a 3, 4, 5 triangle, this would have the same magnitude. We can also talk about the direction of the vector in terms of an angle. So how are we going to do that? Are you playing on your phone? Oh, I'm so offended. Thanks for putting that away. Yeah, why don't we use some right triangle trig to find the angle? Now, where are we going to measure our angle from? This is something that gets kind of, depending on your context, it's not always the same thing. Where would you guys like to measure the angle from? Well, the origin, from where though? I need it in the past when we were doing unit circle stuff, we were always measuring from the positive x-axis. Do you want to continue doing that? Okay, we'll go ahead and do that for this problem. Sometimes, a lot of times when we're using vectors to represent directions, like a ship at sea, we'll measure it from due north and we'll measure it going clockwise around. So you just have to you got to know your context. But we'll go ahead and say our direction from the positive x-axis. Can you guys set up an equation that you could use to solve for that? That's trying its best to be a little theta. Let's use the 3 and the 4 here. We'll be rewriting a sine, a cosine, a tangent equation for this. Tangent from theta, we've got opposite and adjacent, agreed? So that would be a tangent equation. So if I were looking for the direction, and we'll want a calculator here in a minute because we're going to do a decimal approximation for this, but I could set up an equation, tangent theta equals, would it be 3 over 4 or 4 over 3? TOA, opposite over adjacent, 3 over 4. Tangent theta equals 3 over 4. And my assumption is that you remember how to solve that. Do y'all remember how to solve that? We're going to do an inverse tangent. And for the sake of simplicity today, I'm going to say let's work in degrees. So I'm going to check and make sure that I'm in degrees here. Oh, my battery is super low. I just gave away my backup calculator, but hopefully it will make it through here. Good afternoon. How can I help? Mm-hmm. Okay. He said he could take it, but he's not trying to. He said I feel like I'm trying to avoid it. Okay. Is he going home or? Okay, that's fine. Thanks for letting me know. Yeah. Yep. Yeah, if you could bring, he's got one of my calculators. If you could leave that with somebody or. Awesome, thank you. All right, I did inverse tangent. Were you guys able to come up with about 36 points, 36.9? So we're not going to spend a bunch of time going over solving right triangle trig equations, but if that's something that you need some help with, just get my attention. You'll be doing it a bunch, okay? So any questions on finding the magnitude and the direction at this point? Okay, I'm gonna throw some stuff at you today and it's gonna seem like a lot and it's gonna seem kind of wishy-washy, just fair warning. It's gonna take us a couple days, but a couple days of class, but we will kind of pull this all together. We'll look at it kind of algebraically today. We'll look at it graphically when we come together on Thursday. This is all going to start to gel eventually, okay? But for today, we're just soak in as much as you can, okay? I'll give you lots of good examples that are going to be very similar, which you're going to be practicing in the homework. So, okay, so let me give you some different representations of vectors. There's three in particular that we're going to be talking about. So I'm writing representations. I should write a little bit bigger, sorry. There's arrow representations. There's component or wedge representations. That should be a G. And then also unit vector representations. All right, part of your challenge here over the next couple of classes is just getting used to some new notation and language around this stuff. And like any time that you've got to get used to new notation and language, it's going to feel a little uncomfortable until you have done it enough that it just kind of starts feeling natural. So, all right. So arrow notation is going to look a lot like rays in geometry. So for example, you might have something like PQ with a little arrow over top of it. P and Q are going to both represent points. We have some names for these. P, whatever P is going to be the initial point. And then Q we would call the terminal point. Yeah, I like that you're thinking P over Q. And I could use any letter that I want here. So it could be A, B, or C, D, or anything like that. So I just randomly chose P and Q. They're capital letters, so they're going to be points. So we'll do an example here in a minute where we'll do A, B, and I'll give you coordinates for A and I'll give you coordinates for B, and we'll figure out what direction this thing's facing and how big it is. So I just need you to know that it's going to start at a point and end at a point. For example, the vector that we drew right here, we had it starting at 0, 0. So 0, 0 would have been my initial point, and then 3, 4 would be my terminal point. Hey, sorry you're not feeling well. We'll get it done another time. This is the same vector, although it's starting at a different point and ending at another point. We'll talk about how that works. In just a second. All right, next up, component or wedge. This is where I'm going to give you, and we saw an example of this. I'll give you something like, what did we do a second ago? Was it 4,3? And when I'm giving you the 4 and the 3 inside of these wedge notation, which is why we call it wedge notation, the 4 is representing the x component, and the 3 is representing the y component. So those of you who've done physics and free body diagrams, remember how you were always trying to break things down into x and y components? And a lot of times with free body diagrams, you're making sure that the x components all added up to 0 and the y components all added up to 0. If that sounds familiar, that's kind of what's going on here. All right, the unit vector, this is the one that my students tend to feel a little uncomfortable with at first anyways. I'm going to give you an example of what this looks like, and then I'll define what the pieces mean. So for I, this is a lowercase I, but I'm putting an arrow over top of it. Plus 3j, this is a lowercase j, but I'm putting an arrow over top of it. It is important that those i's and j's are lowercase. This is one of those weird things where this looks different in handwriting than it does in text. Like, so if you were to type this out or look at this in a textbook, it's going to look a little bit different. Okay, so these are just lowercase i's and j's with an arrow over top of them. And different people have different styles of how they write this, by the way. So it's not like there's one right way to do it. Some people will go I with a dot and a full arrow over top of it. Some people will go I with a full arrow and no dot over top of it. The important thing is it's got an arrow and it's a lowercase I. Okay, so I kind of do it this way because laziness, less things I got to do. But you may find other ways to write it. As long as I can see it's an I and a J with an arrow over top of it. Now let me explain to you what those are. So I and J are unit vectors. I is defined as a unit vector strictly in the x direction. Now, unit vector means it has to have a length of 1. When we say unit circle, that's a circle with a radius of 1. Unit vector is a vector that has a length of 1, a magnitude of 1. So I in the x direction would be 1, 0. So take a minute and picture, if I asked you to draw that vector, what would it look like? And the x direction would go to the right by 1. It doesn't go up or down at all, correct? And its length would be 1. So that would be a unit vector strictly in the x direction. And then J, anybody want to guess what J is? It's 0, 1. It's a unit vector in the positive y direction. There is one other unit vector. It's not a unit vector. There is one other special vector that comes up from time to time. It's called the 0 vector, and it's denoted as a 0 with an arrow over top. Again, full arrow, half arrow, doesn't really matter. Anybody want to guess what the 0 vector is? 0, 0. It's the only vector that has a magnitude of 0, and it has no direction. Or its direction is undefined. Great question. Why would you need that? Because in math, we need a 0. No matter what we're talking about in math, we always want to make sure we have a 0. So it does come up, believe it or not, from time to time, that unit vector becomes handy for us. All right, so this is all getting pretty cerebral. Let's do some concrete examples here, okay, and try and pull some of the stuff together. I'm at the bottom of my page. I don't have enough space. I'm going to want about half a page for what we're going to do here because we're going to pull a couple different things together. So I'm flipping over and making a new one. Let's define 3 vectors. I found in the past that my students initially feel a little bit more confident with the wedge notation. So we'll stick with that wedge notation for today. And at this point, actually, we're talking about points. I'm going to give you, we're going to define 3 points. A at -8, 3, B at 4, 2, and C at -5, -1. And we're going to do a little work with a few vectors here. So the first vector we'll be looking at will be the vector AB. So I'm using arrow notation here for this. And I'm going to make 3 columns here. So AB, let's also do BC. And just for fun, let's also do CB. So I would like for us to use the information we have to go ahead and write the vector AB in wedge notation. So remember, we don't have this graph, but I want you to envision that this vector is going to start at A and it's going to stretch to B. So how is it moving in the x direction? What would the x component of that vector be? It's positive. It's going from an x coordinate of -8 to +4. How far away is that? That's 12 units away. What about in the y direction? If I'm starting at A and moving towards B in the y direction, -1 from 3 to 2 is -1. Now these are kind of easy to think our way through. Should we ever end up with something where we've got radicals or decimals, it might be nice to have a note for how do we find that. What would I do with -8 and 4 to come up with 12? How do you find a distance between 2 values? Yeah, so we're gonna subtract, right? We find it through subtraction. That's how we find the distance between things. And we always go from the second one minus the first one. So if the technical way to do this is I would do 4 minus -8. That's how I would get that 12. The 4 was the terminal end minus the -8, which was the initial end. And then -1 would have been the second y value minus the first y value, so 2 minus 3. I challenge you to rewrite this in unit vector notation. It's not that hard. You're going to have to just stick a 12 and a -1 in there. Remember, you've got to have a plus or a minus between your 2 terms. The fact that this is negative should make that pretty easy for us to do. 12 minus 1j. Do you think we could get away with leaving that 1 out of there? We could. I will write it in. If it's not my final answer, if I'm still working with it, I'll usually write it in though. All right, so far so good. I would also like you to find me the magnitude. Let me show you how magnitude is denoted. The magnitude of AB. Now, there is a shortcut for finding the magnitude. Okay. If you were to make a triangle out of this, how wide would the triangle be? It would be 12 units wide. How tall would the triangle be? It would be 1 unit tall. And these are going to be the 2 legs, right? You're looking for the hypotenuse. So if our equation, our Pythagorean equation is a squared plus b squared equals c squared, right? If I'm really interested in what c is equal to, what is c equal to? It's the square root of a squared plus b squared. Some of you have worked that out and you've been using that for years to shortcut your way to answers with the Pythagorean theorem on your calculator, right? So I want us to start using this and get in the habit. So to find the magnitude of a vector, you just take your x coordinate, your y coordinate, square them both, take the square root of that. So if I wanted to find my magnitude, I'm just going to do my x component squared plus my y component squared, which happen to be 12 and -1. And actually, I will usually ignore the negative because we're squaring it anyways, right? So that negative is going to go away. So that would be the square root of what? 12 squared plus 1 squared, 144 plus 1, 145. 145. Does that simplify? What's 145 divided by 5? 29, and 29 is prime. So that's, yeah, so that's it. So the magnitude is square root of 145. Yay. All right. All right, your turn. Could you do the same thing for me for BC and CB? Let me know if you need a hint. Good afternoon. I almost said good morning. It's morning in Hawaii. Aloha. You know what you're looking for? How are we going? A to B, oh, B to C rather. And well, that's an interesting question. What do you guys think? So before we're even getting started here, we've got some interesting questions. You're talking about the magnitudes. So we've got a hypothesis that maybe the magnitudes for these two vectors might end up being the same. And you were talking mathematically, said since we're going to be squaring negatives, then they should end up being the same. Would it make sense if I had, what's the difference between these two vectors? I guess the initial point and the terminal point switch, right? So BC would be pointing, it's more negative in the X than it is in the Y. It could be something like that, right? What would I need to do to my pen to make it into CB? I just flip it. It's going to be the same length. It's just facing in the opposite direction. So does it make sense both mathematically and logically that these two vectors are going to have the same length? Yep. Cool. I like it. What a great question. So CB would be -9 squared plus 3 squared. 81, 9 is 90. Root 90, I think we can simplify that. I know a perfect square that goes into 90. So you guys have convinced me that the two magnitudes would be the same. I didn't actually do the work to solve both of them. Did anybody do the work to find the magnitude for each? It is the exact same. It would be the same because we're using, could I get your guys to pause the side conversations for right now, please? Since the X and the Y components are exactly the same except for some changes in signs, but the magnitude equation, we're squaring those things. So yeah, it would make sense that it's the same. All right. What do we want to do next? All right, I'm going to lay something on you guys here. We're going to continue using these same 3 points here. And I'm just going to copy this down here just to have it closer to what I'm going to do with it next. So I'm going to copy down AB. Nope, thank you. AB, we came up with 12, -1. No, it's okay. Is there a question though? No. Okay. We feeling okay? Yeah. Okay. Any questions before we move on? All right. So an excellent question came up a minute ago. Why do we need a zero vector? Right? It doesn't seem like it would be that useful because it doesn't have any direction or an undefined direction. It has a magnitude of 0. What's that useful for? Well, because this is math and we got to do math with these things, right? And when 0 is important in math. So it was an excellent question. So what kind of mathy type things could you think of that we might be able to do with vectors? What do you do with normal numbers that we might be able to try with vectors? We can multiply them. Yeah. We do that all the time with normal numbers. 2 times 3, you know what that is, right? What do you think happens when I multiply a vector times something like 2? So let's check this out. So we have to think, and as mathematicians, what would it mean to take a vector and multiply it by 2? Remember, a vector has a magnitude and a direction. Do you feel like multiplying a vector by a scalar like 2 should change the direction? No. Do you think it should change the magnitude? How do you think it should change the magnitude? It should double it? Okay. So if you had to guess how we would accomplish multiplying something like 2 times a vector 12, -1, what would you guess we'd do with all those numbers? You think we're just going to multiply this 2 times both the X and the Y components? Does that make sense to you? Right. This is what mathematicians, the first person who sat down and started thinking about vectors had to come up with the answers to these types of questions. So I don't know. Let's try it. Let's try it. If we did it, it would be, what would it be? 24. I don't know why I'm writing it backwards. It's happening a lot today. 24, -2. Agreed? Okay. So do me a favor right now, and can you go ahead and find the magnitude of that? And let's see if it does end up being double the magnitude of the original one. The original one had a magnitude of root 145. So I'm going to try and find the magnitude of 24, -2. Let's see here, 24 squared plus 2 squared. I'm using my calculator here because I don't want to, it's 580. 580. 580. 580 is divisible by 4, I believe. It is divisible by 4. That's 4 times 145, which is, oh my gosh, square root of 4 is 2, isn't it? Is it double the magnitude? I'd say, yeah, this one was root 145. This one's 2 root 145. If we're not convinced, we could try doing a decimal version of this and a decimal version of this and making sure it's double. And it does. It does. So whoever suggested that we just kind of distribute or multiply the scalar times all of the components, it seems like it's working. It does work. Well, we also said it needed to be in the same direction. Can somebody convince me that this is going in the same direction as the original, which is, I guess, right here? How do we do direction in like algebra 1? Because these things are like portions of lines. How do we measure kind of the tilt or direction of a line? Lines, think back to algebra 1. Think simply here. How do you know if two lines are parallel back in algebra 1? What do you look at? Yes. Someone said it over here. It has nothing to do with intercepts. It's a slope. The slope tells you how tilted a line is, right? If these two things have the same slope, then they should be facing in the same direction, or at least maybe opposite from one another. Would they have the same slope? If I did rise over run here, am I going to get the same value if I did rise over run here? Yeah, because here I'm going to get negative 1 over 12. Here I'm going to get negative 2 over 24, but that reduces to the same fraction. Agreed? Can you guys stop with the balancing act? I appreciate it. I'm afraid someone's going to fall back and crack their skull open. Thanks. All right. So we can multiply by something like 2. We can actually multiply by any scalar that we want. What do you think happens if we were to multiply by, say, a negative value? Do you think that's possible? What if well, any negative value can be boiled down to a number times negative 1, right? So let's try multiplying AB times negative 1 and see if it behaves like we expect it to do. If I tell you I'm going to take a vector, remember a vector is like an arrow pointing in a particular direction with a particular length, and I was going to multiply it by negative 1. What intuitively, logically do you think should happen to the vector if we multiply it by negative 1? It will go the opposite direction. Length would stay the same, but headed in the opposite direction. So do you think we can do the same thing that we just did a second ago and just distribute that negative 1 into the original vector? Would that result in a vector that has the exact same length as the original heading in the opposite direction? Yeah, it would. So that would be negative 12 comma positive 1. And we've already talked about how since the signs are flipping here, we're just heading in the opposite direction than we were before. So we can multiply by a scalar, positive or negative. Great, we covered that. What else should we be able to do with vectors? Divide, what a great idea. We could divide by something. Now, I would say I've covered the idea that we can multiply by two things. Can we accomplish division using multiplication? For example, if I wanted to do AB divided by 2, that would be the same as AB times 1/2, wouldn't it? And we've already covered that. We said that that's possible. So we can divide. We can multiply and we can divide because multiplication is just division, or division is just multiplication, either way. Cool, so we've covered multiplication, division. What else should we talk about? Addition, subtraction. All right, so let's talk about addition. I need some more space here. I'm going to copy down, again, just for the sake of having these things close by on the same screen. I'm going to copy down AB again, which was 12 comma negative 1. And I need another vector. So let's do BC also. And in our previous notes, we found that to be these. Now, do we want to multiply, or sorry, we're going to try adding. Let's try adding first, and then maybe we can apply what we know about adding to subtraction if we figure something out. Do we want to add a vector with the scalar, or do we want to add two vectors together? You want to try two vectors? So if I did 12 comma negative 1 plus -9, comma, -3. What do you suppose, if you had to guess how we would accomplish that, what do you suppose we would do with those numbers? Okay, the x's and the y's. So you're going to deal with the x's separately from the y's? Yeah, would that make sense? So you're saying add these together. 12 and -9 would be 3, right? And then add our y components together, -1 and -3, -4. Does that make sense to you guys? Yeah, okay. You're gonna have to take my word for it this time, but that totally is how it works. I'll show you why it works graphically when we do that either Thursday or next Monday. Okay, but that's how you do it. That's how you do it. So you can add two vectors together. Now you cannot do this. I'll just throw this out here right now. You cannot do 12, -1 plus 2. You can't add these things together for the same reason that you can't add, for example, 2x plus 5 together. They're not the same type of thing, right? They're not like terms. They're not the same type of thing. So we can't add these together. This would be undefined. But we can add two vectors together, and we accomplish that by just adding the x components together, adding the y components together. Question?
Of like a wedge, like that, almost like its own, variable.
A wedge, kind of like its own variable.
Like its own type of.
Yeah, well, so when we're looking at this, remember this is a vector. We can add things that are like, we're kind of used to the idea of we can add things that are like terms. We can multiply different types of things together. We're used to that. If I asked you to multiply 2x and 5 together, that's not a problem. But we can't add them because they're not like terms. So it's kind of related to that. Yeah, it gets a little bit more complicated than that, but that's a good way to kind of cement that in your mind. So we talked about addition. What if I wanted to subtract? What's an alternate way of subtracting using only addition and maybe something else? We can add the opposite. And how do we find an opposite? We multiply it by -1, and we already decided that we can multiply it by -1. So it seems like we should be able to subtract as well. All right, so let me give you a super complicated problem and have you guys figure it out. We're going to use these two vectors up here. And using this, I would love for you to find me the value of 3ab minus 2bc. See what you can do with that. 3ab minus 2bc. Oh, shoot. I'll show you how I would set up my work, but I've seen people do this a lot of different ways. we able to come up with 54 and 3? Okay, lots of different ways you can show your work. Personally, I don't ever like subtracting because I tend to make mistakes with subtracting. So when I did mine, I just multiplied the first vector times 3, the second vector times -2, and then I just added those two things together. Right? Plus or minus is the same thing as minus. How many people were able to come up with that? That's like the toughest thing you're going to see in your homework. Okay. So if you're feeling pretty good about that, then you got like 60%, 80%, close to 80% of what we got today. Got a couple more things I want to talk about. Any questions about this one before we move on? This is kind of key. If you're good here, then I'm happy. I don't really, if you've got another system on a test or a quiz, I'd love for you to show me some work. So practice how you're going to show me work when you do need to do it. I wouldn't try and pull it off in your head. You could certainly pull it off in the calculator pretty easily, right? But I'd want to be able to see some work. I don't really care how you show me that work though. If you've got another style, I'd love to see it. All right. So yeah, I need you to be able to show me something on a test. So play around with it. See if you can find an easier way to do it. Other questions before we move on? Got a couple small things just to add on here. So at the very beginning, I gave you a vector. Remember, we found the magnitude and we figured out the angle or the direction it was heading. Do you think you could do this in the opposite direction? Let me give you an example of what I'm talking about. Let's say that I tell you that I've got a vector xy. And it has a direction of 120 degrees counterclockwise from the positive x-axis. So that's kind of keeping consistent with how we were measuring angles in the last couple units. And let's say I give you this notation. Did you have a question or something I can help with? Okay. Let me know, guys. Let's say I tell you that that is true. What did I just give you there? Give me a vocab term for what I just gave you there. That's the magnitude. I'm telling you that the magnitude of this vector is 500. Counterclockwise. So that rotating that direction, which is what we're used to for positive angles, right? All right, so what I'm going to ask you to find is, can you write the vector in wedge notation? And while we're at it, let's go ahead and write it in IJ notation. Or unit vector notation. It's just 500 and a period after it. So I'm telling you that the magnitude is 500. End of sentence. So it has a direction 120 degrees counterclockwise from the positive x-axis. And its magnitude is 500. I would like for you to write me wedge notation or unit vector notation. So I'll find this problem a little easier to tackle if I sketch it. So I'm going to go ahead and sketch an x and a y axis. (120 degrees from the positive x-axis). We're pretty comfortable with where that would be, right? What quadrant that would be in. Yeah, quadrant 2 here, yeah. So let's go ahead and draw kind of a rough sketch of something, and it's 120 degrees off of that positive x-axis. So talk to me about my components. Now, I'm not too worried right now about magnitudes, but tell me positive or negative. For this vector right here that we've drawn, is my x component going to be positive or negative? The x component is going to be negative. If I look at this vector overall, in terms of the x direction, you say it's pointing towards the left. If you say it's negative, are we in agreement? I know my x coordinate is going to be negative. What about my y component for this thing? It is going to be positive. That makes sense. So we just need some numbers to go in there. And there is a really strong correlation between this wedge notation and coordinates. It's almost like if I could find the coordinates, the x and y coordinate of that point right there, that would be my answer, wouldn't it? 120 degrees, x and y coordinates for 120 degrees. Why does this sound familiar to me? I feel like we've dealt with x and y coordinates at different angles before, like pretty recently. Maybe again and again and again. You guys didn't throw that sheet away, did you? Can you get it back out for me? This thing's gonna be tattered and taped together by the end. Right? Don't we have like a whole list of coordinates? X and Y coordinates for different angles. So we can do an exact value because we've got X and Y. Now here's the problem though. Dang it. The problem is this is the unit circle, meaning the radius here is what? All of these vectors have a magnitude of 1. We don't want a magnitude of 1. We want 500. So we're stuck. Can we just scale it up by 500? What a great suggestion. How would you do that? We could just multiply it by 500. That would make it 100 times as long, right? And it would be facing in the same direction still. Oh, cool. All right, it's all coming together. Okay, so it's going to be this and this, but times 500. Agreed? All right, let's do it. So I'm going to do some work down here. It's basically just going to be 500 times, and then I'm going to use the coordinates straight from my wheel of fun, good old unit circle. And that's going to get me what I need. Let's do exact values and then I'll let you know. In this unit, go exact values unless otherwise noted. Okay. So the question was, should we round or should we use exact values? So if I do 500 times -1/2, that's going to be -250. 500 times √3/2. So the 500/2 is going to be 250, and then we'll still have that √3 in there. So -250 and then +250 √3. All right, yeah, but that's not too bad. We got to use our wheel of fun. But what happens if, say they give us a problem and they give us an angle that's not on our wheel of fun? What if they gave us something like 123.6 degrees instead? If they gave us 123.6 and it was still 500. So I've just changed my angle to 123.6 degrees. And it's still 500 magnitude. Oh, look at you guys go. Yes. It's still the X and Y coordinates of these points. And we learned that the X and Y coordinates all the way around the unit circle. The whole reason we used this was the X coordinate went with what? Sine or cosine? X coordinates went with cosine and the Y coordinates went with sine. So couldn't I just do this? I could take 500 times and then grab my calculator and do cosine 123.6 comma sine 123.6. Wouldn't that work? Now in that case, we're not going to be able to give an exact answer. So this kind of came from out of your question, should we round? Sometimes if it's like this, we don't really have a choice. We're going to have to round. If they want an exact answer, I'm going to have to say 500 cosine 123.6 comma 500 sine 123.6. All right, one last thing. You guys are doing awesome. One last thing. All right, I'm going to give you a vector here. This comes up a lot in physics and engineering, and we're going to need it for something that we're going to do later on. U is equal to, I'm going to go -3 comma 6. So sometimes they give a lowercase letter with a arrow over top of it. They're just giving you a vector. If it's an I or a J, those are reserved. Those are special ones. But if it's like a U or a V, it can be anything. All right, we are going to find V such that U and V are in the same direction. And the magnitude of V is equal to 1. Super, super useful in a lot of applications, which you'll have to trust me on that. We'll actually see it later on. So U is a vector, and it definitely doesn't have a magnitude of 1 right now. Agreed? Square root of 3 squared plus 6 squared is definitely not going to be 1. So basically, I want to take this vector, which is roughly pointed in, it's -x and +y. It's roughly pointed in this direction. And I want it to make it into another vector that's also pointed in this direction, but I want it to have a magnitude of 1. So basically, I want the same vector, but I need you to shrink it so its magnitude is 1. Okay? And this is super useful because we've already talked about how we can multiply a vector by anything we want to get it to grow it. So if you could come up with a vector that was a magnitude of 1, you could easily turn it into any other vector in that same direction you wanted to just by multiplying it. So that's how this comes up as something really useful. So how are we going to do this? What do you think, Tim? I love it. What a great suggestion. Did y'all hear that? Instead, could we find the magnitude of this one? That would be this vector here. It would be the length of it. Could we just then divide this vector by that magnitude and come up with this one? That would make sense, right? We're shrinking it down, so we're going to divide it. I'm going to say instead of dividing, we'll multiply by a reciprocal, but same idea, right? So yeah, that's totally the process. So first we need to find the magnitude of U. So go ahead and practice this. You're going to be finding so many vector magnitudes. You're going to get really quick with these. You'll be doing them in your head before you know it. Nine plus 36 is 45. And that simplifies. Question is, should we simplify it now or wait until after we've divided? What do you guys think? Any ideas? Let's simplify now. We could always use the other version. Give me a perfect square that goes into 45. 45 is 9 times 5, so square root of 9 is 3. Square root of 5 is root 5, so 3 root 5. All right. So that's the first step of the Timothy method. The second step of the Timothy method is to take that U vector that we had and divide it by the magnitude that we just came up with. Okay, and what I'm going to do instead is I'm going to multiply it by the reciprocal. So instead of dividing, I'm going to multiply by 1 over 3 root 5, the vector u, which was, what was it again? -3 comma -6. Was it negative? No, it wasn't. It was positive. Thank you for that correction. And then we'll simplify all that out and we'll be good to go. So what's that going to be? Well, it's nice that that's a 1 on the top. So it'd be -3 over 3 root 5, comma 6 over 3 root 5. And we're going to need to rationalize and simplify. I think I'll simplify first. 3 over 3 would cancel, so that's just -1 over root 5, comma 6 over 3 is 2 over root 5. Go ahead and rationalize those, come up with good, proper calculus ready answers. Rationalize, simplify, that's what I'm calling calculus ready.
You don't teach calculus.
I haven't for a very long time. Miss Unger is teaching calculus this year, but she won't be here next year. I probably won't, but we've posted 2 new math teacher positions, so we'll be hiring a couple of new people. So more than likely one of them. So we'll start interviewing here sometime soon. I heard we got like 20 some applicants, so that's pretty awesome. I don't know, it depends. Depends on what the rest of the schedule looks like. I love calculus, it's awesome. All right, that's it. I mean, have we done what you said, Timothy? This is your method, so yep, we took the vector, we divided it by the thing, and we've got this. So here's the so the Timothy method. Let's make sure it works. Our original vector was -3 comma 6. If you were to do a slope on this vector, rise over run, what are you going to get? Rise over run, what are you going to get? -2. You're going to get a slope of -2. Agreed? If you're going to do a slope on this, are you also going to get -2? Oh yeah, so we're heading in the right direction. Now the big question is this thing have a magnitude of 1? So last thing I want you to do for me today, please find the magnitude of this. We think this is V, and it definitely is going to be if the magnitude is 1. So this is going to get a little messy because we got radicals and fractions and all that fun stuff. But we're going to find the magnitude the same way we have with all the other simpler vectors that we've done today. Take the square root of the x component, the y component squared. Well, let's simplify it. When you square a fraction, you just square both the numerator and the denominator. What do you get when you square the numerator of this fraction? 5. What do you get for the denominator? 25. Plus, what do you get when you square this? Now remember, you got to square both the 2 and the 5. So 2 squared is 4 times 5 squared is, or root 5 squared is 5 all over 25. I think this is going to work, isn't it? That's 5 over 25 plus 20 over 25. I think that's 25 over 25, aka 1. Are we convinced? Beautiful. So we found V here. And you guys are awesome. Okay, so your homework assignment, you're going to be doing a lot of just kind of messing around with these vectors. I know from experience that you're going to walk out of here today and you're like, okay, I understand how to do this stuff, but I don't really understand what I'm doing. That's where I'm expecting you to be at right now. I chose to kind of start with the algebraic stuff just so you could kind of get your feet wet with the kind of the mathy part of it. But we're gonna be drawing these vectors and seeing what it means to actually add and multiply them. What are some things that we did not do today? We added and subtracted two vectors. We multiplied a vector by a scalar. We have not multiplied two vectors before or yet. We're going to get to that. That's going to require two whole separate sections. So that's one of the more complicated things we're going to do, because it turns out there are a couple different meanings of what you mean when you multiply two vectors. There's something called a dot product and a cross product. Anybody who's taken physics, remember what cross product is? Did they teach you the right-hand rule? No? All right, well, we'll learn all about it later on. Okay, that's what we got for today. Would you like to know your homework assignment? I'll tell you what, I'm going to give you a couple options for the homework assignment today. They're both on page 511. You may either do 1 through 37 odd and 39, 41, and 43, or you can do 1 through 43 odd. Your choice. It is on Canvas. I know. For some reason, I had it written out this way, and I wrote that for my students on Monday, and they were like, "Isn't that just 1 through 43 odd?" It sure is. I recommend the second one. All right. I didn't give you a ton of time, but at least crack open your books and have a look at the types of problems you're going to be doing here. And then let me know